Hello. The main objective of the present lab is to study the projectile motion of an object tossed near the Earth's surface, integrating observations, theory and computational modeling. For the purposes of the 5th physics laboratory, I studied the motion of an object tossed with initial velocity v from height h above the Earth's surface. I analyzed the video of the motion using tracker in order to extract the object's position and the corresponding time, and based on the physics principles I constructed a computational model predicting the motion of the object. Subsequently, I compared the predictions of the computational model to the observations made with tracker by presenting the display window of the VPython the predicted and the observed motion of the object. I also plotted in the graph window of the VPython the energy forms computed by the model. According to the results of the lab, the constructed computational model predicts well the motion of the projectile. While the object moves, its energy changes forms between potential energy due to gravity and kinetic energy. The total energy of the system ball Earth is decaying according to the work done by the drag force. Moreover, the main results of this lab state clearly that computational physics is reshaping the way calculations are made in physics and expands our ability to solve problems and to make progress into physics research. Consider an object tossed from a height above the ground as shown in the figure. The air resistance is considered negligible. The net force along the x-axis is 0. Applying the momentum principle, we have the shown equations for the velocity and the displacement along the x-axis. The net force along the y-axis is equal to the weight of the object. Applying the momentum principle, we have the shown equations for the velocity and the displacement along the y-axis. At the maximum height of its trajectory, the velocity of the object along the y-axis would be 0. Based on this, we can calculate the time at which the object will be at the maximum height. Replacing this time to the position equation along the y-axis, we can calculate what the maximum height of the object will be. Furthermore, setting the position equation along the y-axis equal to the initial height of the object, we can calculate the time needed for the object to reach at its initial height descending. The calculations are made more complex as the forces become non-constant. Now, in the problem studied earlier, let's consider that the air resistance exists. Applying the momentum principle, we have the shown equation. There may or may not exist an analytical solution of this differential equation in terms of well-known mathematical functions, but any differential equation can be solved numerically. In the previously studied case where there was no drag force, we were able to obtain an analytical solution, a prediction for any time of the motion of the object. However, in many cases the differential equation corresponding to the derivative form of the momentum principle has a mathematical form that cannot be solved analytically and must be solved numerically. The power of the computational modeling and the iterative application of the momentum principle is that they can be used even in those situations where no analytical solution seems possible. I enriched the visualization of the model by representing the exerted forces and the velocity of the object with arrows. I also created a second red bar for visualizing the observations made with tracker as they are imported from a properly named CSV file. I set the initial position and velocity of the object according to the observations made with tracker. I was based on the iterative application of the momentum principle for predicting the motion of the object, and I specified the energy forms to be plotted in the graph window. I plotted in the graph window the kinetic, the gravitational potential energy and the total energy of the object as a function of time. I also output the predictions of the model for the position, the velocity and the energy forms of the object versus time into a CSV file. Here is the model when it runs. The red ball represents the data extracted with tracker. Note that the drag force is always opposite to the velocity. If the drag force is zero, while the object moves, its energy changes forms between potential energy due to gravity and kinetic energy. However, there is no change in the total energy of the object. Since there is no significant interaction between the system and the surroundings, there is no work done, and subsequently the total energy of the system remains constant according to the law of the conservation of energy. If we consider the existence of the drag force, then the change in the energy of the system is equal to the work of the drag force, which is always negative, since the direction of the displacement is always opposite to the direction of the drag force. That means the total energy of the system is decreasing over the time. Thank you for your attention.